Hello everyone. Welcome to part 5 of our Fungible token series, where we're building an ICRC compliant token and explaining how it all works in the background. I want to thank everybody for joining us again. Thanks for all the people who since last week minted ICDV. That really helps us. If at the end of this you decide you want to go mint some ICDV, you will get a 1000x bonus at the moment to go to our site and mint it. What are we going to do with it? I've had a ton of ideas in the last week. Hopefully we've got some stuff coming fairly soon. This is a toy token that we use inside of our charity to track cryptographically if you've donated to the charity. And then we may do some fun things with your balance as well to prove social credit or other fun things that we might do. We might do some test DAOs with the token later. So if you want to fund public goods on the internet computer, please consider minting ICDV. It's a fun way to do it. Today, I'm going to give a couple updates on what we've done with ICDV, and then we're going to take a step deep into the code and look at ICRC-2 and ICRC-4, which are two more ways to move tokens around. First of all, let's go over to our donations page, and you will see the results of our video from last week, where we can log in with Plug, click our Mint ICDV button, send ICP to the charity, and get ICDV back in return. We're trying to think through different ways to incentivize people and what we're going to do, and I wanted to be disciplined in how we minted ICDV and how we used it, but I also wanted it to be a resource that we can use that is social credibility inside the ecosystem. So we've updated the minting algorithm. And now when you mint ICDV, you still get your ICDV, but we're also going to mint the same amount of ICDV to the ICDevs treasury, where we can do fun and interesting giveaway type events where we can incentivize developers or reward developers or encourage other people to help developers with the ICDV token. Our total supply was up to about 83,000 ICDV. So we went ahead and minted that treasury, all of that. We basically doubled that. And this does, in theory, double the eventual maximum total supply. But it's a good mirror of the community to the charity that allows the charity to have something to work with. And if you watch our Twitter over the next few days, you should see some of those ways in which we're going to give away this ICDV. I'm just going to run you through the code really quick. So we have our ICDV token project here. And we are going to look at token.mo, and we went and added 2 functions this week and modified one other function. Here we have our mint from ICP function. In the past, we did our transfer from, and when that was successful, we minted tokens to the person who sent them. We added this section here called treasury tokens, which is just the exact same code, except that we changed the to amount to our treasury account. So now we get, if you go and donate 1 ICP, you'll get 1,000 ICDV, and ICDevs will get 1,000 ICDV as well. We added 2 functions just to sort of try to keep tabs on everything. The first was a stats function, and these are queries, and they run very fast, and they just return some data back. So the bonus is the bonus epoch divided by the bonus denominator. We also added our total supply and the number of holders. We also added a holders function where you can pass in a min and a max balance, as well as a previous and a take. Now, previous only comes into play if we have a lot of items and it takes more than 2 megabytes to fill that space, and we want to pick up on page 2, we can pass in a previous. So we're going to have to get over 1,000 holders of ICDV before this becomes an issue. Here, we set up a vector. We see if we're looking for a previous or not, and set that equal to the previous item that we're looking for. Figure out what our take is. And then we're going to loop through the entries in the ICRC-1 get state accounts. And all we do is check a few values. If we haven't found it yet, if we have found it and the results are over the take value, we exit by breaking the function. Otherwise, we check to see if this is the item that we're looking for, and then we'll set be found equal to true and continue. Otherwise, we'll continue the search. We check our min and our max. I believe that this is 20 million E8s, which I think is far beyond the maximum supply of our token. And then we search to see if the item is within a range. And if it is, we add it to our results. And at the end, we just output the results. Well, if we go to the dashboard, the ICP dashboard, and put in our canister ID, we can query our stats very quickly and see that currently minted 83,470. The Treasury ICDV doesn't affect this minted amount. So there's still going to be the opportunity for you guys out there to get that 1,000 bonus for another 917,000 ICDV. We currently have 21 holders. Now we also added that holders. So here we can say, just give us everybody. And it's going to output, this is a JSON view of this. It's going to output these accounts and it's going to show us what everybody's balance is. Now, interestingly enough, these balances are also in the order in which the account was created. So this is interesting because if you want to do something like show me the first, let's call 5 because that's more realistic. We'll see that now we only have 5 items here, and those are the first 5 people that minted ICDV. We can also do something that says, so we want people who have a minimum of 5, just under 5,000. So we're gonna take the first 5 people that have a balance over 5,000. And so we get these 5 accounts, and these folks have over 5,000 ICDV. Again, thanks to everybody who's done that. Now let's dive into the meat of our tutorial today. And today we're going to look at the ICRC-2 standard as well as the ICRC-4 standard. Why not 3? We're going to save that for another video. ICRC-2 and ICRC-4 actually have to do with fungible tokens. ICRC-3 is a log format. So I'm going to stick to tokens at the moment, and we'll look at ICRC-2. It's great to be able to send someone your tokens, but sometimes you want a service to pull tokens from you so that nothing goes wrong and they're able to provide you the service once the tokens have been delivered all in one atomic transaction, or at least all in one atomic call. What ICRC-2 does is it adds the ability for you to approve a spender to spend your tokens. This might be an exchange that you could place a permanent order where you'll say, hey, if someone offers 1 ICP for 1 chat token, I will always take that deal. I will approve you to transfer from my balance. Now, you really only ever want to do this with a smart contract that you trust, with a smart contract that is open sourced, and with a smart contract that has been either black holed or put under the control of a DAO. You should not ever do this with a contract that has not open sourced their code or that has not put their contract under control of a highly unlikely corruptible scheme. If it's not your code, then it's not your contract, and you shouldn't be trusting it, and you certainly shouldn't be approving it to transfer funds from you. Now, that being said, ICDV is exactly that kind of contract, and you really shouldn't trust it. Because it's a toy token, I hope you'll give me a little bit of space. You certainly should never approve our contract to take more from you than you're willing to donate from our charity. The same goes for other contracts. Don't approve more tokens than you're willing for them to take, because they will take them. And sure enough, in our ICDV contract, as soon as we see an approval, we take the funds and consider it a donation, and there's no way to get it back at that point. Let's walk through the ICRC-2 document first, and then we'll go look at the code. So it's a two-step process. The account owner, Alice, entitles Bob to transfer X amount of tokens for her. Now, Bob doesn't have to transfer them to himself. He's authorized to spend those tokens somewhere else. So if it is something like a DEX, they can move the tokens from you to the person who has provided the other side of the trade, and vice versa. They'll provide you with the funds from the other person. So step 1, approve. Step 2, Bob calls transfer from. If I award Bob the right to spend my tokens, he can't give it to Eva. Another thing that's interesting is that you can approve as many tokens as you want. Now, this is theoretically at the implementation level, so you may have some ICRC-2 contracts that only let you approve up to your balance amount, but generally, so far, most of the contracts have allowed an unlimited amount of approval. There may be subscription services, and again, if you trust the other contract because it's black holed or it's under control of a DAO, and it's not going to change its code, you can know that it will only ever take 30 ICP from you per month, because that's the contract you've agreed with. You can read the code, you can see it. Once a month, it may take 30 ICP out. You don't have 30 ICP, when it tries to transfer from, it's going to fail, and it may cut you off of your subscription. So we see in the motivation here, we talk about recurring payments, uncertain transfer amounts. This also just really helps with the workflow. A lot of problems we've had on the IC, especially when it comes to moving tokens and doing something in exchange for tokens, is a user would have to transfer the tokens to your canister. Then they would have to tell you that the tokens were there. This is a two-step process. And if the second process failed for any reason, the other canister had your tokens and you couldn't do anything to get them back. You had to hope that that canister had a refund function on them. What are our methods? We have ICRC-2 approve. You pass into this the from sub account, who the spender is going to be, that's an account, the amount of tokens that you want to approve. There's a cool feature called expected allowance. You don't want data to move out from underneath you. And if you have a distributed system that may be asking for approvals for, or offering approvals for a number of different things, you may want to increase your allowance. Well, if you pass this expected allowance, you can say, hey, I don't want this to go through unless the allowance amount is exactly 5 ICP. You don't have to put an expected allowance in, but if you do, it keeps you safe. There's an expires at, so you can time limit these. If you say, hey, I'm gonna authorize you for 30 ICP this month only, and it expires at the end of the month, you can set that expires at. There is a fee for these. It's usually the same fee as a transfer. Doesn't have to be, but it can be. We have a memo and a created at time that does transaction deduplication, just like ICRC-1 that we looked at a couple lessons ago. Now, there's a lot of reasons that it can fail. We have our errors here. Transfer from is called later by Bob. The spender sub account is provided because up here you can approve a spender to be anyone, specifically a account, which can be a sub account. So you still can have some separation of concerns here in smart contracts where you want to have a sub account for a different sub account for different people. If your smart contract can represent a lot of different individuals, use that sub account to maintain a separation of concerns so there's not a bug and not a mix-up, and you don't commingle funds. You specify where the funds are coming from, where they're going to, and the amount. You can put the fee in as well as memo and create it at time for transaction deduplication. Now, one thing you do have to keep in mind here, when you transfer from, there has to be at least one fee left in the person's account. So if you just put one ICP in your account and then authorize someone or approve someone to spend one ICP, the transfer from will fail when they try to move one ICP. If you are building a service like this, you need to remember to include the fee in the user's authorization. So if you need to pull one ICP, you need to approve 1.001 ICP. Both fees come from the sender. Allowance is a query method that lets you see if an account and a spender has a current allowance or not. And so if I'm Bob, I can say, hey, has Alice given me an allowance? And you'll get a result back saying, yes, this is the allowance and this is when it expires. If you support ICRC-2, you should put ICRC-2 in your ICRC-1 supported standard results, as well as ICRC-10, which we'll talk about another time. We then see some examples and how Alice can remove her approvals. To remove your approval, you basically reapprove, but with a value of 0. That will update the approval to 0 and delete it from the allowance collection. ICRC-2 is much shorter than ICRC-1. So let's go look at the code that we've used on the ICDV token. Let's start up top. ICRC-2 underscore. There's a default max approvals per account, which is 10,000. What you don't want is don't want some rogue canister just filling up and filling up and filling up your collections and burning your cycles. So this is an important way to limit the number of approvals per account. You can limit the max allowance through this contract, either to a amount or to a total supply. Here you can never approve more than total supply. The fee is determined by the ICRC-1 fee. We don't have any advanced settings. The max number of approvals in our contract looks like it's 10 million. If we ever reach 10 million, we're going to delete the 10,000 oldest or smallest items. We set things up just like we did ICRC-1 with some init args. We have our migration state that's a stable value in our state. We set the current state. We have a function to get the state as well as to get an environment. Now what goes into an ICRC-2 environment? Well, you have to pass it the ICRC-1 control class. So it uses ICRC-1 under the hood. So you need to pass your ICRC-1 class into ICRC-2 because that's how it's going to move tokens. That's how it's going to know what the balance is on all the accounts. And we'll see that when we get deeper into the code. We don't have a different fee function, and we don't have anything in here as far as these overrides like we had in in ICRC-1. You can override the approve and transfer. Say you wanted to do something like you can never approve more than half of what's in your account. It's a function of the balance. Well, that's not built into the library, but you could easily add a can approve function here that would look at the balance in the account and the amount being approved and reject it. And then we go get our class here. Now we're at our token actor top level functions, and they're really simple. You just pass the args through into your class and everything should work. Here's our allowance query. Here's our approve function. Here's our transfer from function. Let's go deeper and we will walk through the source code. So I'm going to start looking at our types file. We have a number of libraries that we use underneath the hood. We have this ledger info, which we looked at those settings. You can set the max approvals per account. You can set a total approvals for your entire class. You can set a max allowance or null. You can set what the settle to is, as well as your fee. You have a stats object where you can pull this information back. So indexes are used for fast access to data. If you're looking for an approval inside of just an array, what you would normally have to do if you have 10,000 balances would go from front to back and look for your account. Then once you found the account, you might have an array in there where you would have a number of spenders for that account. And you have to loop through that array. So you might end up having to go through 10,000 records if you have 10,000 accounts and then 10,000 spenders on each account before you can find your record. These indexes will hold data that will point to other records and therefore will help us get to our data faster because they use clustered indexing and have lookup tables inside of them. We can get to our data a lot faster. Here in the stats, we're just returning how many records are in each of those. As far as the fee goes, we can have a natural fixed fee. We can use an environment variable, which is that get fee function that we saw, or we can default to whatever the fee is for ICRC1. Same for max allowance. There's a default for total supply as well as one for fixed. It doesn't make any sense to approve more than the total supply, so you can cap it at that, or you can set a fixed max. If you set it to nothing enforced, there is one thing that you should consider. Natural numbers are unbounded. So someone could make an allowance for a comically large number, and that could use up a lot of your cycles. So you probably want to add some checks and balances throughout this code to make sure that you don't allow someone to push that kind of data into your library. Can transfer from and can approve are our overrides. We can create a function that gets passed the value as well as the operation value as well as the outer envelope of the block value, a notification with some details about the transfer from or approval. And we can then override those. We can change them and return back different values, and the function will pick up with those different values. We have our approve args, our errors. We have a type for updating our ledger, our responses. We have a number of comparison functions that we pull in from ICRC1. We have event listeners as well on this class. So if we want to listen for transfer froms and listen for approvals, then we can do that as well. So say our service wants to mint you an NFT if you issue us an approval and it still exists 10 days from now. When you get the notification, you can set a timer to come back and check and then issue that NFT. These approval hashes and approval equals functions are used to create maps of approvals. Here we have our indexes. We keep a spender to approval, so we can look up very quickly by spender what accounts have been approved, and then we have an owner to approval, so we can look up what accounts have been used from an owner's perspective. And then we have our state, and our state in ICRC2 is pretty small. It's just our constants, our map of token approvals, and then our indexes. So let's go to our class that uses all of these types. We pull in some types from our class. We have this transfer from listener. We have a token approval listener. And we get all this set up until we get to our class. Remember, this is a class plus setup, which means that each time your canister restarts, the state is stored elsewhere in a stable variable, and when you reconstitute your class, you need to hand the state back to the class. Once you've handed the state back to the class, you can call the class just like you would a normal class. This really helps you by not having to do a bunch of stuff in your pre and post upgrade. You'll notice in our token contract, I haven't done almost anything in pre and post upgrade, except maybe wire up a few listeners. So here is our class. We have our state. We set up these private variables to hold our listeners. We can hand out our ledger info. We can go get our indexes as well if we need to look at those. We can get our state. We have our metadata. ICRC1 has a metadata call. This function will go through, when we initialize our metadata, it will go and inject some of these interesting variables from our class into the ICRC1 metadata as well. Once this is done, you'll know if there's a max approvals per account, if there's a max approvals, a lot of this information that you might want to know if you're consuming this. Say you're a wallet and you want to provide the same rules that the ledger has, and you want to tell the user, hey, you just tried to approve more than the total supply, you can't do that. This would provide that information from the ICRC1 metadata endpoint. We have a get fee function. This will either return a fixed value, the ICRC1 value, or call another function to construct the fee out of a function that you provide. We have a helper function to validate our fee. We validate the approval by checking the calculated fee and looking up here in our token approvals by our account. Here we're checking for the expected allowance. So we go look up in our map this particular allowance, and then we look to see if if our current request has an expected allowance or not and compare it. If they don't match, then we can return an error. We have to do some other tests, like testing the memo's not too large, testing that the expires is not in the past, checking that the from and the spender aren't equal. You're not supposed to approve yourself. Doesn't make any sense. We check the number of approvals. We test the created at to make sure that you're within the proper window. And we probably, I think deduplication is done at the ICRC1 level later. Similar function to validate transfer from. We're going through and validating the transfer from, validating the sender. We're checking the balance by going into the environment, pulling ICRC1 and checking the balance of the person that it's coming from. So if you don't have enough tokens to transfer, tokens plus the fee to transfer, then we're going to reject it. So we get that insufficient allowance. Then we have the top level approve function, which calls a lower level function. We're going to validate the approval. We're going to get the amount to use based off of some information here. This is where we call the override. Here we're determining the amount to use based off of whether or not you set a max allowance or not. Then we again test our memos, test our expires at, all of those things. We're building our block here, adding all of the items that make up an ICRC2 block. We then use the find duplication in our ICRC1. If we've implemented ICRC3 inside of ICRC1, it'll use that pathway inside of ICRC1. If it's a local just test token, then it'll use the local transaction log to deduplicate. Once all that's put together, we're going to construct our token approval notification and eventually pass it into can approve if it exists. Now again, we can call both synchronous and asynchronous functions here. If we call an asynchronous function, when we come back, we have to revalidate everything to make sure that data hasn't changed while we were waiting for our response. We burn our fee. We handle any fee collector information that may be in the block, and then we transfer the balance. We should end up with the transaction ID. If we've spent some of the approval, then we need to update that approval amount and update our index with any new information that we may have. A lot of this will look like ICRC1. We're doing some of the same things, like cleaning up our recent transactions. And that's our approved transfers. A few more helper transactions, a lookup transaction that will go and get the allowance. We have a cleanup expired approvals routine that can run on a timer. We can unindex items. Here's our cleanup function. It's going to go and check different criteria, like has the expired at passed. If the expired at is passed, we can remove those items and we can unindex them and remove them from our collection. If we do hit that 1 million approvals, we can call this system clean function and it will go and clean out items. Any items that it does clean out, it does log to the transaction log, which is an interesting feature. So we want that transaction log to be able to reconstruct the entire state later. Here's a function you can call to register your listeners, a generic function, and then we use that generic function here to register the token approved and the token transfer from listeners. This is a function we use to update data inside of our ledger if we need to change these max approval values later on. We have a token transferred function here, but we're not doing anything with it right now. This library might need to be updated so that it goes through and removes any allowances that have gone to zero. We're not currently doing that. They'll be cleaned up later if necessary. Here's a transfer tokens function that's called by transfer from. A lot of the same, and eventually it will call into ICRC1 and move. If we get past this can transfer from stage, it's going to go and actually move the tokens. We have to take care and make sure we deduplicate our transactions again and add transactions to that queue. These others are just sort of helpful entry functions. We can get our stats, initialize our metadata. And when the class finishes up, it initializes its own metadata and registers the supported standards in ICRC1. And that's really it for ICRC2. It looks a whole lot like our ICRC1 function. And now we're going to go look at ICRC4, which really looks like our ICRC1 setup, because all ICRC4 is batch transactions. ICRC4 has not been approved by the NNS yet, but it's in a fairly advanced draft stage where it's been reviewed by the working group and is ready to go forward. What has to happen next for ICRC4 is for the security group at Dfinity to go through and look at it and see what the attack vectors are, how it can be used to stall any existing ledger. Especially when it comes to ICP, you definitely don't want anything that can go in that could cause that to have serious issues. And so every time we add one of these standards, we try to do an implementation, and Dfinity usually does an implementation on the ICP ledger or on the SNS ledgers, and then it eventually gets rolled out everywhere. Now, because ICRC4 is basically approved by the working group, we went ahead and implemented it because we wanted to implement it and know that it's working and have a test bed. The best way for us to test this stuff out is for us to do it on toy tokens like ICDV, and then to move it to the next stage, and then to the next stage, and then eventually into ICP. Now, I don't know when Dfinity is going to get time to do ICRC4, but once they do, it's really going to help with a lot of use cases. Let's take a look at the standard, see what it does, and then we'll take a look at the code. So we're just extending ICRC1. So in ICRC1, with every call, you can move from one account to one other account. Well, that's great, except that you have to wait 2 seconds to get your response back from the ledger, or 6 seconds, depending on what subnet you're on. And if you have to loop through a lot of items, that can take a long time. Even if you are able to write a script that does it sort of in parallel, each message has its own ingress costs. And there's a lot of repeated stuff that goes on. So if you can send a lot of transactions in one function, not only do you get responses back faster, but you only have to pay that ingress message or that cross subnet cost once. A use case here would be something like paying royalties on an NFT. If you have a large set of royalties, like you want to reward the creator, the maybe previous owners, you want to reward a community treasury, you want to reward a network, you want to reward the brokers and the marketplaces, you may have 5 or 6 or 7 different royalties that you want to pay. It's much easier to batch all those up in one call, get the results back, and make sure that you've paid all the royalties than to have to do them one at a time. There's a bit of a section in here about batch update methods. And the texture of this is based off of how the internet computer works. And you'll find the same pattern in ICRC7, which is batch by default for NFTs. They didn't even do a single NFT transaction. They just went ahead and did batch from the very beginning, because if you only want to transfer one, then you only provide one in the batch. Now, because canisters are asynchronous, and you may have a function that you want to do that depends on something else, you can't be assured that every single item will be addressed or that it will be atomic, meaning in a case where you have multiple canisters, it's almost impossible to write code where either all the things work or none of the things work. Say you want to, like ICDV, you want to mint some tokens to users who helped support a developer who sold some NFTs. Okay, so the developer sold some NFTs to finance a project. We want to support that, so we're going to create a function that will mint ICDV if you hold one of the NFTs. Well, we have to make a call over to the NFT canister to get that balance. So if someone says mint to these 8 accounts, and they pass us 8 items, and we start processing them in order, and then the NFT canister gets upgraded while we're in the middle, depending on how we submit them, or which ones got there first, cross subnet barriers, we may have some of them succeed and some of them not. And so our batch update methods provide for that. They also provide for a scenario where you look at the first message and it's doing something illegal and you don't want to finish the rest. So if you give us an illegal memo that's way too big and it's going to be a burden and a burn on our system to even go through and process the 100 transactions you just sent us, the canister has the ability to reject right then and only provide you one response as opposed to the 100 responses that you asked for. So how that works, here you can see inputs A through H. It's possible, if the messages are processed out of order, that you may have a null value in one of the slots. So your results are going to be in the same order as your requests, but some of them may be null. If we got to a certain point and we did something later, say we did the 8th item first for some reason, and it failed for a major reason, we might give you the error in the 8th spot and report null for the first 7. So there's also these generic batch errors, and that's where when you hit a generic batch error, that may be the last item. If you process something beyond that and it was successful, you still need to report it, but you can always stop with the generic batch error, and if you do, you assume that the rest of them that are not provided are null. Similar with query methods, your responses are all going to be in the order of your requests. If for some reason we didn't handle it, there may be a null. So now, what functions do we have inside of ICRC-4? Well, there's transfer batch. Transfer batch is fairly straightforward here. You provide a vector of transfer args. So the same thing you pass into ICRC-1 transfer, you pass into ICRC-4 transfer batch, but in a vector array. So if you want to transfer to 5 different accounts, you provide 5 different transfer args, and the transfer args are exactly the same as they are in ICRC-1. In your transaction log, you're going to see it as 5 individual items on the transaction log in the order that they end up being processed. Keep in mind your response will have the responses coming back in the same order that you requested them, but that does not mean that the blocks will be in the same order unless your canister is written that way. Generally with ICRC-4, the best practice is to have the same fee as you do with the ICRC-1 token. In theory, it costs a bit less because you're burning fewer cycles to do some of this stuff, but ultimately, because you're paying for storage, we suggest that you do the same fee that you do for ICRC-1 times the number of requests. Just like you have transfer batch, you also have balance of batch, which lets you check the balance of many accounts at one time. There is a metadata item called maximum update batch size and maximum query batch size, which will tell a wallet or an indexer or some other service the maximum number that they can request at a time. On the internet computer, you can't return over 2 megabytes of data in a response, so you definitely want to keep it under 2 megabytes, but sometimes even that is just a lot of processing to do to kind of block your canister while you're doing it. So it's, set some reasonable amount, 100, maybe 500, maybe 1,000. But if you get too big, you risk hitting that 2 megabyte limit. There are no changes to the block schema. There's no ICRC-4 block. What you will see is ICRC-1 transactions in your transaction log. You do transaction deduplication. You send 100 of the same transaction, only the first one's going to get processed. The rest of them should hit that deduplication. If you need to repeat it 100 times for some reason, you need to provide a unique memo for each one. And that will help it to avoid transaction deduplication. If we go over and look at our code for ICRC-4, I guess we're starting up at the top level, so we'll look at our token for ICRC-4. We see it has init args, and in our ICDV token, we allow 200 batch transfers at a time, as well as 200 balances at a time. The classes are all handled just like ICRC-1 and ICRC-4, And our environment, again, ICRC-4 plays off of ICRC-1. So you have to pass ICRC-1 into the ICRC-4 class when you instantiate it in the environment. We don't have any extra fee calculation, and we don't have any additional. This is interesting. It looks like there's actually an error here where it looks like it's taking the same parameters as ICRC-2. We have our ICRC-4 transfer batch function, which we just pass straight through into our class and process it just like you would expect. We have our balance of batch, same thing, and then our queries that get our metadata. Inside of our ICRC-4 class, our types are going to look very much like our ICRC-1 types, except we have this new transfer batch args. Maybe some more transfer batch error, some new types of errors, including too many requests. We have our balance query results as well as our query requests. There is a batch notification. There is a batch can transfer. Interesting. So there's nothing passed in here. So those other values that we saw in our class are actually just an error. They're not going in and doing anything, and they're a super type of the actual environment, which just needs ICRC-1 in the fee calculation. Then in our actual library class, again, we set everything up. We pull in the new types that we need. We have our transfer batch listener, which gets notified whenever a batch has been occurred. We have our overrides for can transfer batch or can batch transfer. We set up our initial states, and then we pass in our environment, our state, and the canister that we're running on into our class. We also inject some metadata from ICRC-4 into that ICRC-1 metadata function, like ICRC-4 max balances, ICRC-4 max transfers, ICRC fee. Typically it just says ICRC-1. We can get a different fee if we want. We can validate the batch. Really all we have to do in here is check and make sure the size is not too big. Register a listener, an update function so we can change these values. Then we have our transfer batch tokens. Here we first check this handle can batch transfer. If that comes back, we are going to hit our process loop, and we are going to loop through each of the transfers and handle them one by one. We use a lot of ICRC-1 stuff in here to basically just do the same thing that we're doing in ICRC-1. We burn our fee, we store our transactions, set it up for deduplication, basically just a mirror of the ICRC-1 contract library, except it's happening in a loop. Now we've looked at ICRC-1, ICRC-2, and ICRC-4, which gives us all of our current fungible token endpoints that allow us to move and transfer things. Now with this, we can do bulk transfers. Some services become a little bit easier to write. We'll have to see where we end up using this for ICDV. Right now, if I wanted to, I could, for instance, pull a list of principals that own a particular NFT collection, and in one function call, send all of those principals, or at least up to 200 of those principals, some ICDV, or mint ICDV to them if I wanted to write that function. I hope this deep dive was interesting and you got to see a little bit of how the class works, with a few nuggets of information of why we chose to do certain things a certain way. Please, if you have any questions, let me know. I've really enjoyed doing these videos. I have some obligations over the next couple weeks, which may slow them down a little bit, but there will be more. And I appreciate everyone who has minted ICDV. I think we're going to do some fun things with it, and I think you're going to want some. So be one of the first in line and go get that bonus so we can do some fun things with it and we can fund public goods. The other thing that I wanted to mention is that I'm really hoping that we have something for Gitcoin Grants 20 for ICDevs. And so be on the lookout for that. The donations, I believe, start on the 23rd. That's a different thing than ICDV, but it may be a really interesting way for us to write a tutorial that uses the EVM RPC canister to go see if you donated. So if you can prove that you own and have signed using one of the addresses that donated to ICDevs, maybe we'll mint you some ICDV for that as well. So thank you very much. We'll see if I have time to build that or not. Or if you want to help contribute to ICDV or to ICDevs as a donation and just do that work, it would be an amazing thing to go do for the community, amazing thing to do for the charity, and we would welcome those pull requests. So fork ICDV, write it up and let us know. We'll do a video on it and feature your work. I'll talk to you all again soon.